Okay, so this is going to finish up the section on volumes. I'm going to do a couple more examples from the book, um, and then I will be finished. I plan on posting a few worked out problems from this week just to help you guys out with the homework, things like that, kind of like if you had a recitation. Um, so this problem is example 7 in the book. I've labeled it this time because I cannot draw this. I've tried to draw it here on the left. So the idea is we have a solid with a circular base, and the cross sections of this solid are going to be equilateral triangles. And we want to figure out what the volume of the solid. So we want to find volume of the solid. So again, the idea we're going to use here is one we've been using, that volume is the integral of the cross-sectional area along, let's say the x-axis in this case. So what we need to do is we need to be able to describe what this cross-sectional area is as a function of x as we move along the x-axis. And to do that, what we're going to need to do is we're going to need to recognize, okay, our area here, the cross-sectional area here is that of a triangle. So area of a triangle is 1/2 base times height. And so we have to determine what the base are or what the base is and what the height is. And we're going to need to do that in terms of x in this case, because remember, x is our integration variable. So if I draw a triangle here, so one of these triangles, so the triangle here gets split up, and you can see it a little better in the actual picture that I've drawn above the triangle down there. So the base of the triangle is going to have, some y coordinate here and some y coordinate here. So the base down here is going to be 2 times, the y coordinate here and here. So the base then is going to be 2y there. So you can see it. So let me draw this triangle a little better. So we have actually something that looks like this. And then you can see, okay, yeah, so on the y-axis, if this is the y coordinate, this is also the y coordinate. So on the triangle down here, I have 2 y's. And I need to figure out what the height is. So I need to figure out this height right here. And that's not actually going to be too bad. We can do it in terms of y, and then we'll talk about how to get y in terms of x. So it's okay right now that we're doing this in terms of y, but eventually, because our integration variable is dx, integration differential is dx, we want to put everything in terms of x. So in order to figure out what h is, we're going to have to use a little bit of geometry here. So we're told that this thing is an equilateral triangle. So if you remember that so equilateral means they're all the same, all the interior angles are the same, and you have to remember that, okay, the interior angles of a triangle add up to 180 degrees. This angle here is 60. Now we can do some trigonometry to determine what h is. So the first thing we're going to notice is that tangent of 60 degrees is going to be the opposite side over the adjacent side, and that's going to be h divided by y. So this tells me that h is equal to y times tangent of 60 degrees. And so now we need to determine what tangent of 60 degrees is. So tan 60 degrees, this is sine of 60 degrees, divided by cosine of 60 degrees. This is square root of 3 over 2 divided by 1/2. This is the square root of 3. And I've run out of room here. These whiteboards are really small. So let's go ahead and make a new page and bring the relevant information. Area is 1/2 the base times the height. Base we said was 2y. Now height we have is square root of 3 times y there. Okay, so now we need to put, so now we have, our area function in terms of y. So area function is in terms of y. We needed an x. So we're gonna have to, so for this one, we're gonna have to look at, so let's go back and look at my picture. So in order to get y in terms of x, so I use the, so I'm gonna use the fact that I have a circle down here. So I'm gonna use the fact that, down here, it's a circle of radius 1. And so what we can do is we can write down the equation for a circle of radius 1. So this one is easy to remember. X squared plus y squared is equal to 1 squared. And of course, 1 squared is just 1. So this will allow us to now solve for y in terms of x. So we're going to go ahead and do that. So we're going to get then y is equal to the square root of 1 minus x squared here. And now, because we're talking, we want all these things, we want all these things to be positive, because we're looking for this area, so this volume to be a positive thing. We're going to look at positive quantities only. I'm going to ignore the negative square root. I can now put all this together. I find that, so putting all this together, I'm going to find that area is 1/2 the base times the height, which is 1/2 times 2y times square root of 3y. And simplifying, the 2's cancel, so I'm going to get radical 3y squared. And when I plug that in, I get square root of 3 times 1 minus x squared. And now that I've determined my area here, so I have an expression for area that is in terms of x, all I have to do now is do the integral. So this volume then is the integral area dx. So this is going to be, and you have to ask yourself, okay, what values does x run over? So let's go back to my drawing. So remember, this is a circle of radius 1. So this point here is 1. This point here is 1. This point here is 1. That point there is 1. So if you look at the x-axis, we want we're going to integrate these triangles all the way from -1. Sorry, these are negatives. So this is -1. This is -1. So from -1 to 1 in this case. So that gives me bounds on my integral. And now I get the integral square root of 3 times 1 minus x squared dx from -1 to 1. This is an even function. You can use that symmetry. This is 2 times, pull out the square root of 3. The integral from 0 to 1, 1 minus x squared dx. And the way I know this is an even function is, so if you look at this here, it's a polynomial, and all of the factors of x appear in even powers. Here is an x to the 0. Here is an x squared. So because all my powers are even powers of x, I have an even function there. So I can use that symmetry, and I just get that factor of 2 out front, and it makes the integral a little easier. Okay, so let's finish this integral on the next page. So I have 2 radical 3, integral from 0 to 1, 1 minus x squared dx. And so we're just going to do this. 2 radical 3, x minus x cubed over 3. We should be getting good at this by now. 0 to 1. So when I plug in 0, both of those terms are going to be 0. So this is just 2 radical 3 times 1 minus 1 cubed is 1, 1/3. This is 2 radical 3 times 2/3, which is, so 4 radical 3 over 3. And I guess I can cancel a factor of radical 3. I get 4 divided by radical 3. And that will be my final answer there. So just to recap, so for this one, we always start at the same place. We want some sort of area. We want to be able to determine some sort of area based on these cross sections. And to do that, I just look at the geometry. This time it was triangles. So area of a triangle is 1/2 base times the height. I looked at one of these triangles and I said, okay, well, if I draw one of these triangles in terms of X and Y, well, then the triangle, so the base of the triangle is just, whatever the whatever Y coordinate I have, I get 2 of them because it's cut in half. And then from that, so that gave me the base. And from that, I needed to figure out what the height was. And I could just use I could use trigonometry here. Tangent, because I know the opposite and the adjacent sides. I want to find the opposite side and I know the adjacent side, hypothetically. And so from this, I'm able to determine H in terms of Y. So that lets me now, so now that I have everything in terms of Y, I realize I'm not integrating with Y, I'm integrating with X. So I use the fact that I have a circle, and I use the equation of a circle to figure out what Y is in terms of X here. And from there, I just plug that all together, and I get my area function in terms of X, and I integrate that. So pretty straightforward. These problems I know are a little difficult, but when you do a few of them, they begin to make sense, But this idea of trying to find the area and just integrating it, that is all that we're trying to do here. So let's do another example. So there are a bunch of these in the book. And these are all fun to draw. So I have an x-axis here, a y-axis, and I have a pyramid with a square base, it looks like. I think it's square. It's square or rectangular? Square. So square base. So I'm going to get something that looks like that. So it's square with side L and height H. So square side L, and the whole height of this thing is H. So let me redraw it without the axes. Oh boy. No, that's not going to work. So maybe, okay. Sorry, my art skills are that of a 5-year-old. So length here, and I have a height H there. So now I want to figure out, okay, I want to figure out the volume of this. We want to find the volume. Okay, so in order to find volume, again, it's going to be, volume is the integral area. And again, I imagine as I'm going, the direction I'm integrating is along the x-axis. So in this case, it's dx. If I were, if the figure were going, if the solid were going in a different direction, you would do a different integration variable. But this determines what we want things in, what variables we want to use here, x. And then we have to determine the cross section. So, if you imagine taking a slice out of this, you can already kind of see, I'm going to have squares here at any slice. But the size of the square changes as I go along the x-axis, which is why I need to do the integral, because things are changing with respect to x. Okay, so we need to determine the area here. So the area then is the area of a square. So area of the square is just, whatever so this one is going to be, so it's not, so you might be tempted to write down L squared first, but that's not the area. So that's the area of the base here. But you can see that, if you go away from the base, that the squares get smaller. So I'm trying to think of a good, so if I look at this square here, you can see that, what this is going to be is, if I look at this left-hand side here, and I'm going to do yellow apparently there for some reason, what this is going to look like, this side here, this is going to have a height y, this is going to have a height y, whatever my y coordinate is there. And so I could just do area is y squared then. 2y squared, sorry. So this is going to be 4y squared. But now I need to put this in terms of x there. And the way I'm going to do that is I'm going to use some geometry. I'm going to use the idea of similar figures. So there's similar triangles here. So if I draw this triangle here, I know I'm running out of room, but if I draw this triangle, let me erase that. All right, so I have a triangle. The idea is, this here is going to be my 2y. And this distance here let me erase that. Sorry, I'm just trying to keep things. This here is x, this is y here. Well, this is 2y here. Here is L, and this is H. So now I have two, because these triangles share the same angle down here. I know that the ratio of the lengths to the heights to the bases are going to be equal. So that tells me that x over 2y is going to be equal to h over L. Now I want to solve this for y because I need to do everything in terms of x. So if I do that quickly, I'm going to get y is equal to x L over 2h. And now I'm going to put this all together on the next page. So I have area is 4y squared. And my y was, already forgotten it, xl over 2h. So my area then is 4 times xl over 2h squared, 4 times x squared L squared over 4h squared. This is x squared L squared over h squared. Okay, so now my area function, my cross-sectional area is in terms of x. I get then that my volume is just the integral a dx, and this is equal to the integral. And if you look along the x-axis, so look back at my picture to figure out the bounds of the integral. So on the x-axis, I start off at 0 here, and I go down the entire height of the cone there, the pyramid there. So my integration bounds are from 0 to the height of the pyramid. And then I get x squared L squared over h squared dx. Now this is an easy integral to do. L squared over h squared, integral 0 to h, x squared dx, pull out the constants, L squared over h squared, x cubed over 3, integrated or evaluated 0 and h. This then is L squared over h squared, and then I get an h cubed over 3 minus 0. So then this is L squared h over 3 for my final answer. So again, these problems all follow the same pattern. We can do a recap of it if you want me to go a little slower over it. So we want to find the volume. Volume is always the integral of the area dx, where the area of these cross sections depends on x usually. You can see that, as you go along the x-axis, these square cross sections are getting larger. So that's why we're integrating. So if you look at this picture here, you can see that each side of so on the left side of the triangle, whatever my y coordinate is, that's half the height. So I get a y here and a y here. So my area then is 2y squared. I add those together and square it. That's why there's parentheses around there. So in order to get y in terms of x, in this case, I have to use the idea of similar triangles here. So over here, I've drawn the triangle. Let me erase that red line so we can see what I've done there. So the first triangle is the one with height x and base 2y. So it's just I've gone along the x-axis a distance x, and then my y coordinate is 2 times, or my base is 2 times y. So I have a height of y. Oops, sorry. I have a height y up top. So I have a height y here, and I have a height of y there. So that gives me 2y, and then the other triangle that I'm looking at is the one that extends all the way down. We know the height of the entire pyramid is h, base is L, and that allows me to set up the ratio here, x over 2y, so height divided by base has to be equal to the height divided by the base of the larger one, h divided by L. That allows me to solve for x. That allows me to solve for y in terms of x, and then I take that and I plug it into the area here, and then that gives me an expression to evaluate or to integrate to get the volume, and that's what I've done here. I've just finished out the integration. So this video's gone on long enough. I'm going to stop it here. This will be the end of section 6.2. I'm going to put up a video of just some example problems from all the sections. I'll segment them, so if you're not really interested in seeing what the example problems for U substitution, that's fine. You don't have to watch them. So I'll just do it in terms of sections. All right, so I'll stop there.